Great.
Good, thank you.
Okay, once again, thank you for the introduction. I have a rather long title, but let's see what I will manage to cover in the next 25 minutes, because I want to leave some time for discussion. First of all, let me and there is a little issue with that I think I have to out now to accept your this. Okay, does that work now? Sorry, the record message goes behind the screen and wants a response. Okay,
so they're not displaying anymore, Adrian. Sorry.
Sorry, that was because I had to come out and try this. Let me just try again. Share. Is that now sharing?
Yeah, all good, and it's on the thanks page.
Okay, right. And I put this up at the start so that we don't forget at the end. I really want to thank people, particularly here over the years, who have been working on some of these problems. Shirin Nui, Maya Helsing, Vasilis Kapaklis, colleagues in Lund, and I will try and say something about some recent work from Caroline Matanda's PhD dissertation. She was working with Tommy and Christelle Prince, and I was interfering a little, and people at facilities who have been helping us do these experiments, ISIS, MLZ, ILL, and NCNR. And this really requires a lot of effort from all of these people to do it. They weren't put down as authors because they haven't reviewed what I'm going to say. I take the blame for the presentation. They can take the credit for doing all the hard work. So I want to really stick to talking about GSANS, or near surface SANS, today. We've heard a lot about neutrons and X-rays and complementarity. Photons are nice, and we also work with X-rays, but I think it's time to really emphasize some of the points about GSANS, what needs development and where we can go. And the general challenges with grazing incident small angle neutron scattering is getting enough signal, whether you've got enough material to scatter, whether you've got enough neutrons in the instant beam. There are also issues about background and resolution, and I will highlight some of these with some examples from various studies that we've made. And in looking at this, what is the signal? What can we understand or interpret? What is ignored? We often just identify a feature and then don't say anything about the rest. And this leads us on to the question, what can we really detect? How sensitive is the technique? Because we've seen various experiments, particularly if you go to just reflectivity measurements, a few hundred nanograms of material can give you your signal. And this is really attractive and so on, but there are also a lot of challenges in how to analyze data, signal above background, what's the resolution, how do we calculate? And I will perhaps say a few things, some a little bit old, some perhaps a little bit controversial, and I'd like to have some discussion on those. So the important thing is that often we think of surfaces as just being two-dimensional, a plane. Really, an interface is a three-dimensional object, and we have to think how deep we're going, what the structures are, both in the plane and out of the plane. And this is really an important part of studying interfaces. Why would we use surface neutron scattering? I think we have to be very clear that when we're going to use an expensive tool like neutron scattering, it's because we're going to study systems that we can't look at with other techniques. So we're going to exploit the contrast available with neutrons, and we've heard in previous talks about isotopic labeling, about magnetic scattering, and so we're going to really be using those techniques, and we're also going to be using it to study samples that we can't just look at with a microscope. We can't slice up and put in an electron microscope necessarily, because they're fragile, they're maybe liquid samples, they're in delicate equilibrium. And I realized that there are a lot of different people represented in the audience, people who are just using or trying to use the technique. They're instrument scientists and facility managers, and there are different emphases that people put on this. Everybody wants to get exciting science out of the instrumentation. But let's look at some experiments. Let's give you an example or two. Why use near surface or grazing instant scattering? Well, perhaps the first thing is we can look at the cover of two theses from Sala, and I'm going to show some of the work here. And both Maya Helsing and Shirin Nui chose to put some surface scattering on the cover of their theses. It's not just because it looks nice. Obviously, they do look interesting pictures, but you can see that if you've got a pattern such as you have on the left-hand side, you have an immense amount of information in that pattern. You may not know immediately what it's all about. Similarly, on the right-hand side, a series of patterns taken at different angles of instance on a solid liquid interface, and one can see that as you probe at different depths, you observe different features of the structure. And so it's really exciting. There should be a lot of things there, but how are we going to understand all of this information? That's what I really want to talk about. Let's have a look at some older data from Maya Helsing's thesis and some papers. I will give some references as we go on. So this was looking at a very classical surfactant system. I think some of these have even been mentioned already. It's a sodium aerosol OT in water, and it's a very useful surfactant. It's got a fairly well accepted phase diagram from a long time ago, 1969. Rogers and Windsor published the phase diagram. I don't think this has really been improved on very much. The aerosol OT molecule has two alkyl chains and polar ionic head group, and it self-assembles very well. In fact, it self-assembles at many interfaces, air-water interfaces, hydrophobic interfaces, hydrophilic interfaces, and so it's been studied on quite a number of occasions. And this phase diagram can help guide us a little in what we see in some of these things. And if I just show you a little bit about this image that we had on the cover. This is one of many that would be taken when you're trying to measure reflection or scattering. And you can see that we've just sort of highlighted a few parts on this. This was measured at the ILL on the D22 instrument, and you can see that there's a lot of scattering from fairly deep into the solution. There is some reflection. There is you need a scattering peak, and some of the bulk scattering is quite strongly aligned. Now I could show you about 50 of these pictures measured at different angles. So we try and get the reflectivity curve. I won't go through all of the data, but if we try and extract a conventional reflectivity, I'm always impressed at people who can easily extract a reflectivity. We have to think what we're going to do. We have a reflected peak, and people often want to subtract background. We try and do this the best we can, and this shows you some reflectivity curve. And I suppose this really explains why I started worrying a bit about grazing instance scattering, was that reflectivity should be simple to understand. It's telling us about density profile perpendicular to the interface, but if we want to extract a reflectivity profile, we need to know what background to subtract. And it's not always easy to know what background to subtract. People have software to do this, and they will often take an area either side of a reflected peak and perhaps average that and subtract that from the intensity in the peak region. That's not quite the flat earth view of background. It's a straight line view of background, but you can see that from the previous picture that may not be very simple to do. And so there's actually quite a lot of work to assess how to subtract background and get a reflectivity curve like this. I won't go into the detail, but I'll say that when you do get a reflectivity curve like this, it's giving you really an immense amount of information. You can see from the multiple diffraction peaks, the multiple Bragg peaks that arise in the reflectivity, that there's a multi-layer structure. You can determine the spacing in the multi-layer structure, and because you have several peaks, you can actually get quite a good measure of the density and the thickness. You can fit the fluctuations in that multi-layer structure. And this is really telling you a lot about this lamellar structure, much more than you get from a regular SANS experiment, because you've got everything directed, you've got very good intensity. And so I show you some of the parameters that you get from that. And that's quite interesting. The spacings are rather interesting, because the spacings that you get correspond to those that you would see in a 10% solution of AOT, whereas this is measured in a 2% solution. And it's telling us that we're getting pre-wetting of a concentrated phase at the surface. That's really quite noticeable. Actually, I showed you this phase diagram earlier, and I magnified this part of the phase diagram that we've been exploring here, and you see actually there are only 2 points that Rogers and Windsor actually measured here, and they drew some lines sketching it. It's probably quite good, but you can see why you might get a phase separation into a 10%, approximately 10% concentration. But obviously that phase diagram is not so well known, with just 2 points in this corner of the diagram. So you can explore effects of temperature, and you get quite a lot of interesting behavior, and you can see how fluctuations change with temperature. I won't go into the details on that. And you know, this is quite a general thing, and I just show this as another example. This is a different surfactant. It's a non-ionic surfactant, so it's got a polar group that is not ionizable. It's ethylene oxide, and so it has rather different temperature behavior. And we also see a lot of strong layering near a surface. This is a interesting reflectivity curve. You can see the reflectivity is coming up to a little above 10%, about 15% of the instant beam. So this is actually something where, although it's a material that you could inject with a syringe, it's fairly viscous. It's 55% of this material measured in D2O, heavy water. It is something that you could think of using as a low resolution monochromator. I'm certain it could be optimized a little bit more than this. So lots of questions arise when doing this. You know, what do we subtract? What should be fitted? How have we deduced that? And let me give you a very old example of what background looks like, just because even something that's fairly simple poses some challenges. And so again, I go back over 30 years and take some data was published. It was actually Bob Thomas who was doing this, and actually organized that this diagram was drawn, because it was before they had postscript printers at the ILL. It was using D17 as a liquids reflectometer. It shows here at the top the detector intensity on a sort of pseudo gray scale. If we measure the reflection from pure D2O, we see a strong signal. If we take 8% of D2O in H2O, we have what's called null reflecting water, where there is essentially no specular reflected signal, because the scattering length density is the same as air, the refractive index is the same as air. So that was published to sort of demonstrate and show this. So not everybody believed it was easy to do this. But what you do notice is that as you take a line from the bottom of the detector to the top of the detector, there is actually a very strong gradation in intensity. And that is important. Again, this is an indication that the background is not constant, in this case with angle. I'm just plotting channel number here, but you can think of this as increasing angle, and the intensity goes up. And if we take some data from a similar sample, this time measured on Figaro at D17, you can see that essentially we get the same type of behavior. We get an increase, and it reaches some sort of plateau level. You might expect it to reach some sort of plateau because of it's dominated by incoherent scattering from the hydrogen in water. So we see that, and actually it's possible to fit a curve to that. I won't go into this in any detail. That's essentially trying to assume that there is some multiple scattering. It just makes an allowance for twofold scattering if we take a simple expression of this form. And you can see that this line fits quite well. So you could see that just trying to model the background may be important if we're trying to measure weak signals. What I should say is that if you're doing these experiments with a range of wavelengths, you may want to think about the inelastic scattering and how inelastically scattered neutrons are coded. But you will normally find that they gain energy, so that you will find more appearing at what is an apparent larger momentum transfer than you might expect. And we can also do back of the envelope calculations for that, but I won't go into that. But we've seen this equation already just before lunch. Peter Muller-Buschbaum showed this equation, which is essentially how deep is the neutron beam penetrating into your sample. And this equation has been written down a long time ago. You'll find it in many papers. It's normally first taken from X-ray results, and people normally describe this quantity mu as please bear in mind that for neutrons that may not be the dominant term. Mu should be considered an attenuation coefficient. It's really something that, for example, incoherent scattering may vastly dominate absorption. And if we just look at some values that we put in, you can see that the cross-section for the incoherent scattering is quite big. So that's not necessarily the same with X-rays, and so we forgive people for describing it as an absorption coefficient for X-rays quite often, but when people go and say the theory is the same for neutrons, the theory is the same, but do make certain that the approximations are valid. And so when people just go and look up the table of absorption for the neutrons, they may not get the right answer. And that curve is really quite simple, but there are some things that we need to bear in mind when we do experiments. For example, often we work with a wavelength distribution, and this, I think, is the wavelength distribution that was used for some measurements on D22, and we try and use this equation, and we then have to think what will be the penetration for the different wavelengths, because there's quite a broad range here. And if we then average this, you can see that this red line here, which represents something that is really for the distribution rather than just for a mean value, is quite different. And because there is a significant number of short wavelength neutrons in the beam, they will penetrate further into the sample. There will also be a spread of angles, and so this penetration of the neutrons into the sample may be a little bit different the simple curve that we were shown and that Peter Müller-Buschbaum showed, which works very well for X-rays, but perhaps not for neutrons. And actually, because of the low intensity of neutron beams and the weak scattering, it's actually rather rare that one is measuring in this region where you're getting true evanescent wave scattering. You're normally probing some of this traveling wave that is going into the sample. So instrument resolution is crucial. You must know what it is. So let's start looking a little bit more at some of these pictures that we've had. And this is one of the pictures. This was on Shirin Nui's thesis, but it was something where she was also working with Maya Helsing and Vasilis Kapaklis. So put a dispersion of spherical particles next to a solid surface, and let's look at the reflection and the scattering. And once again, you start doing this, and we have a fairly transparent cell, some shielding from some seals and some aluminium frame, but you can see that if we take a fairly large angle of instance, you can see that you get scattering on both sides. You can see transmitted and reflected. We can actually probe at different depths. You can actually look at the intensity on Bragg peaks at different points along this line, and you can see that this will actually fit quite well here. So it's interesting, but it didn't allow us to probe exactly how far these particles were from the surface. Unfortunately, we've not reached that yet, but we do, by just turning the sample round, manage to look at what the structure is in the bulk. And you will have seen that those are very well ordered at over many centimeters. When we look in the bulk, if we take a 2mm diameter beam, you almost have powder rings of diffraction. It's only when you get to a 1mm beam size that you are beginning to see single domains. And so we know that the domain structure, when we go 0.5 millimeter to 1 millimeter into the surface, is different, but we haven't really yet managed to identify from this type of study how close the particles pack to the surface. I might say from other techniques, we know that they are repelled slightly from the surface. Let me just finish with a few words about a different system. This is some silicon nanowires. Thought it would be rather nice to have a solid sample. And this is Caroline Mutanda's thesis work. She defended her thesis last year. Nanowires are fairly cheap. They cost about 10⁻⁵ crowns per wire. Unfortunately, we have 10⁻⁻10 wires on this sample, so the sample is a little bit expensive. But we have a very regular array, and we can actually see nice scattering from that. And you can also do reflection from the surface. And you can add materials such as lipids. And the question that we asked was, how do lipids change when they are on flat surfaces, on curved surfaces? Thing is that you can actually see that there is a difference when you add lipid, both in the reflection and in the scattering. Let me just say that these peaks here are not Bragg diffraction peaks. Let's just think about this. For that spacing of 500 nanometers, one 0 or 0.1 and 1.1 peaks will have a spacing of 10⁻³ angstrom. With the resolution, they're smeared out. They're continuous lines, although the intensity is not uniform over reciprocal space because you do have a higher density of peaks in certain directions. And look at how this changes when you add lipids, and like with many of the other experiments, comparing intensities is really useful and important. And so you can actually compare these and you can get some idea. So the comes out that it looks as though you're getting a very hydrated layer on the wires of about 28, 30 angstroms thickness. Just a summary picture of what you can see from reflection. There is slightly more material on the surface in between, although it is very rough surface, and that arises from making the nanowires. So let me just finish now with some conclusions. There is a lot of information. We've seen lots of interesting behavior. Comparing data sets can give some quantitative results, but we have not really been able to do whole pattern fitting. Considering the background, you have to consider what sort of space, whether you work in detector space or in Q space. Multiple scattering is often important, and depth information you do get, it's mostly in the micrometer range rather than the nanometer range in these types of systems. And so with that, I will stop, and I hope we can discuss this. There are lots of questions that I would like answered.